In our last few lectures, we talked about modes and how the orthogonality of modes could be used to uncouple equations of motion. We used that to solve free response problems, transient free response problems. So if we were given an initial condition in a structure, what would the vibration be? So today we'll talk about how we can use that to solve force problems. So to put this into an application example, suppose we were interested in the vibration of this wind turbine, and let's just say the tower without the blade. We'll leave the blade off for now. So what we've done already with transient response would allow us to solve for the vibration of the tower if we were to come up to the tower and bend it over and then let it go. That's a free response problem. In this lecture, we'll talk about forced response. So imagine that this tower is sitting here, minding its own business, and the wind blows. And we could model a gust of wind as a step increase in force. So in an instant, the force goes from 0 to some non-zero value that wants to bend the tower over a little bit. And for a large tower that might be 100 meters tall or more like this, you could have maybe a meter of deflection at the top of the tower, maybe more, in a reasonable wind. So that's the problem that we're going to try to model. We'll use our favorite 2 degree of freedom example again, just to keep things nice and simple. And so this is a 2-mass system with 3 springs. We have unit masses, unit springs, so we have these mass and stiffness matrices that we've seen before. And we've already reviewed the fundamental equations that we use to transform from these coordinates, physical coordinates q1 and q2, which are the position of the masses, to modal coordinates, eta. And we basically plug this into the equation of motion. We use the orthogonality properties to show that our system of equations becomes diagonal. And on the right-hand side, we get the mode shape matrix transpose times the force. Let's look in a little more detail at what happens. If we transform the mode shape matrix like that, that means that this top row, this is what used to be the first column, or this is the first mode. And similarly, this bottom row, that's what used to be the second column, or that's mode 2. So then, in this case, we've assumed that the force is applied only to mass 1. So, say this was our wind turbine tower, and we've discretized it with 2 degrees of freedom, and say we call this one mass 1 and this one mass 2. Not a very good example, because if this was the real wind turbine, we wouldn't have that spring right there. But anyway, the idea is that a gust comes along and applies a force only to one of those masses. So when we look at this multiplication here, what it does is we get the mode shape transpose times the force. So that's going to just end up taking the first element times the force. The second element of the mode shape, or the mode shape at the other mass, is irrelevant. So it just multiplies 0. So what we end up with down here is the mode shape at the point where the force was applied. That's what ends up scaling the force. So we end up with these 2 uncoupled equations. If we wanted, we could write those out in more detail, just in case you're struggling with linear algebra here. So the first equation would be eta 1 double dot plus omega 1 squared there times eta 1, and that would be equal to phi 1, 1, the scalar, times f of t. And then we'd have a similar equation for mode 2. So we need to solve both of those equations, and our initial conditions will say if the displacements are all 0, then the modal displacements are all 0. So this is just a a forced response. And if we say that f of t is a step function, so let's say that in time our force looks like this, where it's 0 before time 0, then it suddenly comes up, and then it's a step, and then it stays at a constant value of, and let's just have it be a unit step, so we have, say, 1 Newton of force. So if that's the case, this is the unit step response. And if we go to the book to Appendix B, we could eventually find that force in the appendix, and with a little bit of manipulation, we can rewrite it in this simpler form right here. The expression given in the back of the book is a little more complicated, but basically we have 1 due to the forcing, 1 over m omega squared. That gives us like a k term. So that says that we get a static response of f over k. And then we get this dynamic response that has a decaying term due to the damping, e to the negative zeta omega nt. And then this is the oscillating part with amplitude a. And the complex amplitude, it has a real and imaginary, or like a sine and a cosine part. But anyway, so that's our step response. And in the most general case, the response to that step, I'll flip my colors around here, but the response might look something like that, where it's going to steady out at late time into the free vibration, or the static response to that step force. Okay, so notice this Q is a function of the natural frequency, the damping ratio, and time, and also the mass. But if we leave the mass out, then we can write this as natural frequency, damping ratio, and time. Now we have to use this correctly, we have to recall that this equation in the book, this equation was derived for the case where we had Q double dot. Let me make that a little bigger. That was derived for the case where we had a differential equation that was Q double dot plus 2 zeta omega n Q dot plus omega n squared Q equals 1 over m, actually they have a capital M there, times f of t. So there's that almost matches with our equation here, but not quite. Our equation, instead of 1 over m, has phi 1 here. So to make this match, we're going to scale the force. We're going to replace the force, F naught over m, with our constant phi 1. So the response that we get would be, for eta 1, would be scaled by phi 1 here. And then we'd have the mass in that equation to cancel the m in the denominator, and then we would use Q step. And this part is exactly the part from Appendix B. So that would be the solution for mode 1 as a function of time. The solution for mode 2 as a function of time is exactly the same, only we replace the constant out front and the natural frequency with that from mode 2. And then we have both of those responses we can plug back in to the equation that we started with up here to get the response of each of the masses. So this right here, this will be the response of mass 1 and mass 2 versus time. And as we mentioned before, it's just a superposition of the two mode shapes, the two mass normalized mode shapes, so I probably should have written them like that, times their respective modal coordinates. So that's all there is to it. Once we've understood the transient response, there really wasn't that much new here, right? So let's see what this looks like in MATLAB. So there's an example file on the website. You can see the name there, Transient with Forced. And basically, the first part is exactly like what we looked at last time. We define the mass and stiffness matrices. We define any initial conditions that we want to use. And we solve the eigenvalue problem. And if we run this script, we'll just look at what we get as we go that far. So the top part just gives us the mode shapes matrix, the two natural frequencies, and then we did a check here to make sure that the modes did diagonalize the mass matrix. We could do the same thing with the stiffness matrix. All right, so that was what we had last time. What's new if we want to do forced response? Well, I'm going to change my initial conditions to be zeros. And so these are the initial conditions on the Q's. Those don't get used anywhere here because I've only done the solution here for for the forced part of the response. But all we have to do is define a time vector, or figure out what instance in time do we want to know the answer at. And then I program in a function here that I call the unit step response. That's the QS of t right there. So I've just put this into MATLAB. It's a little sloppy because I wanted to write it all on one line. But we have the scale factor, the 1 minus e to the negative zeta omega n t. I'm using dot multiply because t can be a vector of time instants. And it will do this operation at every time instant all at once. And then of the real part, this is my complex amplitude term, e to the I omega dt. So in our case, if damping is 0, a lot of this simplifies down. But I might as well write it general so I can use it again in the future, right? So now we can define eta as a function of time. And what I've done here is I've defined eta to be a 2 by number of time samples vector. So it's the top row will be eta 1, the bottom row will be eta 2. And so eta 1 is just that constant times the step response of t with here, this is the first natural frequency. Now we can do the second thing for mode 2, the same thing for mode 2. It's the response, it's the mode shape at the first mass where the force is applied of the second mode. And then we put in here the natural frequency of the second mode. And so this gives us, at each instant in time, for example, eta t of colon comma 10, this would be the 10th time instant. These are the values of the two modal amplitudes. So at each instant in time, if I wanted to get back to physical coordinates, I would just take that answer and I'd multiply it by the mode shape matrix. And this would tell me where mass 1 is and where mass 2 is. If I want to get the response of the masses as a function of time, I can do that all in one line with MATLAB. Just multiply x of t is phi times eta. That will do this exact same computation at every column or every instant in time. And so on one line, I get back x as a function of time. So we can see all of this in the plot that we get here. Oops, wrong one. We can see all of this in the plot that we get right here. So in modal coordinates, we get eta 1 as a function of time eta 2. So here we have an offset due to the static term, and they end up going in the negative direction because the mode shapes MATLAB gave were negative at the first coordinate. But that gets taken care of later. But anyway, the vibration, we have a new steady state, a new static equilibrium position due to the increase in force, and then the vibration is happening about that position. And mode 1 and mode 2 have the same kind of form, they just have different frequencies and different scale factors on that vibration. When we put that all together, though, into mass 1 and mass 2, here we see more complicated things happening, right? We see this interplay. So the force is applied on mass 1, so it starts to move first. And mass 2 is lagging. It only feels the force. If we go back to our picture here, we apply a force to mass 1, it starts to move. Mass 2 doesn't start to feel anything until this spring compresses and pushes on it. So it's delayed, and then finally we get so much deflection in the springs that mass 1 wants to turn around and stop moving in that direction and start coming back. Mass 2 eventually starts to feel that, and it responds, and so you get this complicated interplay between the two motions. So in modal coordinates, everything is really simple. It's just the step response of two 1 degree of freedom systems. In physical coordinates, you can get some really interesting and rich dynamics happening there. And so this is our key to understanding forced response for multi-degree of freedom systems. There's one other part of the code that I'll show you here. In case you didn't trust the answer you were getting from this solution, or actually I would do this anytime I was creating a new code to make sure I didn't have any bugs. This little bit of code will call the equation of motion of the forced system. So I've put the mass and stiffness matrix in. I've defined the force to be a unit step on the first mass. And then it solves using numerical. This is the function that would be used that OD would use to solve with numerical integration for the transient response. And I'll add some markers to overlay what I've already put on to show what the response is, what the response of the system is that we get from OD45, and we'll compare that with what we got using our analytical solution. So if I run that, nothing changed, and now I can see the x1 versus x1 from OD45 exactly agree with each other, and the similar for x2. So in this case, either was a good way to solve this. If we were to zoom in infinitely, eventually we might see some slight inaccuracy due to the numerical integration that OD45 is using to estimate this response, where our analytical response is the true response to a differential equation that we've defined. So for a small system like this, both are really fast. But for a large system, there are big advantages to being able to find the response analytically. Okay, so that concludes this example on response of a 2 degree of freedom system using both OD45 and using the analytical solution with equations from Appendix B in Ginsberg's book.